expert insights on AI and NLP. Before we dive into today's exciting session, I would like to invite the Vice Chair of the IEEE Student Branch of Rajarata University of Sri Lanka to deliver the welcome speech. Please join me in welcoming Pramod Rajapaksa. Over to you.
Hello, am I audible?
Yes, Pramod.
Good evening, everyone. I'm Pramod Rajapaksha, as the Vice Chair of IEEE Student Branch of Rajarata University of Sri Lanka. So, it's a pleasure to welcome you all to today's AI Community Talk, organized by IEEE Young Professional Sri Lanka in collaboration with AI Driven Sri Lanka and the IEEE Student Branch of Rajarata University of Sri Lanka. So, our topic today, NLP Fundamentals, Unlocking the Power of Trustworthy and Impactful AI, highlights the growing importance of natural language processing in shaping the future of artificial intelligence. NLP plays a vital role in many AI applications we use daily, whether it's chatbots, translation tools, or voice assistants, and is at the core of make AI both intelligent and trustworthy. We are fortunate to have with us Mr. Ishara Neranjana, a talented machine learning engineer whose knowledge and experience in NLP will undoubtedly offer us valuable insight and spark meaningful discussions. This session is a unique opportunity for all of us to learn, connect, and explore how we can apply AI technology responsibly and effectively in both professional and personal contexts. I encourage all of you to actively participate, ask questions, share your thoughts, and make the most of this platform to expand your knowledge and network. Thank you once again for being part of this event. Special thanks to our organizers and collaborators for making it happen. Thank you.
Thank you so much, Pramod, for those kind words and officially welcoming everyone. Now it's time to dive into the exciting world of AI. We are privileged to have with us today Mr. Ishara Neranjana, Associate Machine Learning Engineer at Zone 24/7, who has extensive experience in the field of AI and machine learning. Now that we have gathered here to explore the fascinating world of artificial intelligence, let's dive into today's exciting topic and hear from our expert as we explore the transformative power of AI in shaping industries and communities. Let's move the floor to Mr. Ishara Neranjana. Over to you, Mr. Ishara Neranjana.
Thank you, Pasna and Pramod. So good evening, everyone. So today we are going to talk about the fundamentals of NLP, which will be able to unlocking the power of trustworthy and impactful AI applications. So first of all, I will share my screen and hope you all can see my screen.
Hello. Hello.
Am I audible?
Yes.
Yeah. Can you see the screen as well?
Yes, Ishara.
Yes, sir.
Okay, thank you. So I am Ishara Neranjana, currently working as a machine learning engineer at Zone 24/7. So let's first look at the agenda for the day. And so first of all, I will talk about the NLP. What is NLP? and the major levels of linguistics, and what is tokenization, and what is word embeddings. And then we will look at the application side of this and understand what are hallucinations. And also we will look at what are the causes for the hallucinations, and then we will see how we can detect these hallucinations and avoid them in our applications. And later we will have a Q&A session as well as wrapping up this session. So first of all, let's look at what is NLP. So let's say that you are typing a quick text to a friend and you mean to say that I will bring dessert tonight. But the autocorrect in your device has changed this message to I will bring disaster tonight. So your friend is now thoroughly confused and you are left wondering how does technology mess up something so simple. So this might seem like a funny everyday moment, but it highlights the fact that the challenge in understanding language. So it is complicated even for machines. So this is where natural language processing comes in. So NLP is the field of AI dedicated to helping computers understand and interact with human language. So think about how often you are encountering NLP applications. When you are talk to Alexa, Siri, or use Google Translate, or even get movie recommendations from applications. So they are actually more accurate these days, and all of these rely on machine understanding your words and the context. Even you are using generative applications like chatbots these days for every task, right? So, but the language just is not just about words. It's about the meaning. So, how does a machine grasp sarcasm or the ambiguity or the slang? So, and what happens? It was not able to identify these things. So as we dive into these fundamentals, so let's uncover how these systems work and what happens when they hallucinate or which is failing, right? So when we talk about NLP, there are two main areas. The first one is language understanding, and the second part is language generation. So first, now when you look at language understanding, so it is the computer's ability to read and make sense of what you are saying. So it's like when a chatbot understand the intent behind your question. So if you don't phrase it perfectly, but the models will be able to identify what you are saying, right? So it is language understanding. And then there's the other side of it, that is language generation. So when the machine understanding what you have been said, so it generates an answer for you. So it is the computer takes all the information it has and it produces human-like responses. So it is in the day-to-day chatbots as well. So together, these two components create a full loop of communication. So understanding is about listening and interpreting, and while generation is about responding. So when you have to create an applications, these two aspects are essential. So if these language understanding and generation are accurate, then the system is accurately working and it is a better system and it is a efficient one as well. So now let's look at when you talk about NLP. So this is an example of how many texts we can process in a minute. So if you look at this one, so here we can see that in a minute. So this is actually from the statistics from 2020. So there are 18.1 million text sent in a minute, and there are over 87,000 people are tweeting, and there are more than 188 million emails sent within a minute, and there are also WhatsApp messenger text. There are about 42 million. So if you look at these NLP area, so there are a lot of data that we can use to build these systems and to get an understanding about the language. So we have enough data to create applications and to create models that are capable of understanding the language. So now let's look at the major levels of linguistics. So when we look at this diagram, so here we have phonetics, phonology, morphology, syntax, semantics, and pragmatics. So, so in when you look at phonetics, so it is the sound of speech. So when you are speaking, the sounds are generated. We call them phonetics. And the studying of these sounds, the area of studying these sound, we call it as phonology. And then we have morphology. These are the words, and then we have syntax. So it is how language generate the sentences and syntaxes. All those are there. And then we have semantics. So it is the meaning of phrases and sentences. And then we have pragmatics. So it is the meaning of the sentence in a context, like in a dialogue or paragraphs. So it is the area that we call that pragmatics. And so here, this is an example how we communicate. So first we have the speech going in, and then we heard this speech as in the phonetic level, and then we have words, lexical level, and then syntactic, which will generate sentences, and the semantic, and then the discourse, conversation, and then pragmatics. It is about the context of this entire conversation. So we need to we are doing this thing always, but without knowing that, right? So if we want to understand how NLP works, we need to know about these levels. And now, in order to understand this language for a machine, we need to divide these words into smaller units, right? So for example, so we call it as tokenization in NLP. So now if we look at this, now we have a sentence. It is supercalifragilistic, so it is quite a lengthy word. So here, if we look at, if we tokenize the sentence, it can be divided as this. So there are smaller units that may be subwords or words or character level. So it will depend on the tokenization model you have been used in the applications of the model. So actually, the tokenization is the breaking these sentences into smaller parts so that machines can analyze and understand the human language. So it is like imagine you are trying to teach a child to read, and instead of diving straight into complex words or paragraphs, you start by introducing them to individual letters, right? Then syllables, then finally whole words. So in a similar fashion, we need the tokenization breaks down the complex words and complex sentences into more smaller digestible parts and understandable parts for the machines. So it is what we call as tokenization. So now let's look at some techniques in tokenizations. So as I mentioned previously, we have word level tokenization. So it breaks text into individual words, and so it is effective for languages like English and French, which have clear word boundaries. So we have in English, we have spaces between words, right? And we have character level tokenization. So it segments text into individual characters. So it is useful for languages without clear word boundaries or tasks requiring granular level analysis. And then we have subword tokenization. So it breaks text into units larger than characters but smaller than complete words. So it is beneficial for languages with complex morphology or handling out of vocabulary words. For example, if we have some out of vocabulary words, it will divide these into subwords and assign a token. And to implement tokenization, we have several libraries in Python. So one is NLTK. So it is an comprehensive Python library for linguistic needs, and it is offering us a word and sentence level tokenization. And we have Space. It is a more efficient one, and it is an alternative to NLTK. And it is a more efficient, sensitive, fast, and supports multiple languages as well. And we have BERT like tokenizers as well, which are using models to tokenize these sentences. So these are some of the methods that libraries that we have or techniques that we can implement tokenization. There are some, so if you look at this diagram here in a model, so let's say we are using a sentiment analysis task, and here we have the input text, and then we need to tokenize this input text that the machines can understand it, and then we need to have embedding layer, and then we have neural network, and then we can get the prediction. So if we look at, there are some advanced techniques as well for implementing tokenization. So one of them is byte pair encoding. So it is actually an adaptive tokenization method that, so this BP tokenized based on the most frequent bytes pairs in a text. So it is particularly effective for languages that form meaning by combining smaller units. And then we have sentence piece as well as word piece. So sentence piece is an unsupervised text tokenizer, and it mainly based on neural networks for text generation tasks, and it handles multiple languages and with a single model. So it can tokenize text into subwords, making it versatile for different NLP tasks. And so this is the diagram of word piece algorithm. So it is developed by Google. And here we can see that I get the next character, and then by matching with the corpus we have of the characters, right? Then if we cannot find a match for that one, so we check whether it stop at a word boundary, and also check whether that text is fully tokenized. And if not, we append the word tokens, and then do this repeatedly until we have finished this entire collection of words. So we call that a corpus. So this is about tokenization. And now when we have tokenized these sentences, so now we have divided the sentences or paragraphs into more smaller units called tokens. And then when we need to identify the meaning of these tokens, we use a technique called embeddings. So that is how machines learn the meaning or the context of words. So when you're talking about embeddings, so it is a method of representing words as a numerical vector. So we can create a vector in high dimensional space so that similar words can represent in a similar area. So these vectors are designed to capture the semantic and syntactic meaning of words, so that allow machines to understand the relationship between them. So unlike traditional representations such as one-hot encoding, so you may have heard in data science and machine learning tasks. So when you have features, categorical features, we do one-hot encoding, right? So it assigns a unique vector to every word. So now let's say we have 50,000 words in our collection. So the length of the vector will be 50,000. So when you're processing these things, it will cost, it is computationally not efficient. So when we create word embeddings, we can reduce the dimension and create more efficient vectors, more small vectors, right? And so, for example, let's say here now we have some examples. When you look at the, so now we have the vector, uh, embedding vector for the word cat. So these are the numbers. And then if you look at the embedding vector for the kitten and dog, so it is quite close to each other. But if you look at the word embedding for the houses, it is quite far away from these two. So now here in this one, this is an 7-dimensional vector, but we have reduced that to 2-dimensional to visualize this thing. And here we can see that if you look at the word man and woman, so here it is quite similar to each other, but you can see the direction. So it is the direction is similar between man and woman and king and queen. So the direction was similar due to the relationship between those word pairs. So we can identify the relationship between word pairs as well as the similar words for some words in a collection. So this helps, the embeddings help for a machine or the model to identify the context and the meaning of these words, right? So it is about the embeddings. And so now let's look at some of the techniques that we have to implement word embeddings. So we have few methods that we can create these embeddings. So now in a few slides, I will tell you that why these embeddings and tokenization is very important when we are creating LLM-based applications or generative AI applications. So here now we have frequency-based embedding methods like count vectors, TF-IDF, and co-occurrence matrices. So in count vectors, we represent text as a vector of word counts, and each word is assigned a unique index, and the vector values respond to the number of times each word appears in the text. The TF-IDF means term frequency and inverse document frequency. So it is a multiplication of these values, and it adjusts the word frequency by considering its importance across documents. So words that occur frequently in a document but rarely occurs as corpus are given higher weights. And then we have the concurrence matrices, which captures the relationships between words by analyzing how often words appear together. So it generates a matrix representing the co-occurrence frequency of word pairs. So these are all frequency-based embedding methods. And then we have prediction-based embeddings. One of these is continuous bag of words, and the other one is skip graph. So now, if you look at continuous bag of words, so it is it predicts a target word based on its surrounding context, and the model takes a window of words as input and tries to predict the center. And in the scriptgram, it is the opposite of that. We have a word and we are going to predict the context word. So those are prediction-based embedding models. And then we have GLOB. So it is a global vector representation. So it is an hybrid approach of the above two techniques, frequency-based embeddings and prediction-based embeddings. And it uses the co-occurrence matrices statistical information with prediction-based optimization. So it builds a global representation of words by learning from their overall co-occurrence patterns across the entire corpus. So here you can see that these embeddings for a corpus in a three-dimensional space. So likewise, this can be n-dimensional, and similar words will be formed together. So now we have talked about the embeddings and tokenization. So now if we have created some LLM-based applications, or when you are using these generative applications, you have seen that sometimes you are not getting the expected answer. So, and actually sometimes they are generating answers that seems correct, but actually they are wrong, right? So why this is happening? So let's look at that. So now in medical terms, a hallucination is a false perception of objects or events involving our senses. For example, uh, let's say it is with the sight or sound, smell, or the taste. So hallucinations seem real, but they are not, right? So chemical responses between or the abnormalities in your brain causes these hallucinations. Likewise, in a LLM, hallucinations occur when a user instruct or given a prompt leads to the LM to predict tokens that are not aligned with the expected answer or the ground truth. So these hallucinations mainly happen either because the correct token was not available or because the LLM failed to retrieve that token. So what are the causes of these? What are the causes that LLMs are generating or generating incorrect data or hallucinate? So there are a few reasons that this could happen. So for example, this could happen due to the lack of scarce training data and lack of alignment. And it could happen due to poor attention techniques, and it would cause due to tokenization. So now let's look at each of these, why these causes LMs to hallucinate. So we do know that for an LLM to learn some knowledge, so it is not enough to show it some information once, right? So in fact, it benefits from being exposed to a piece of knowledge from diverse sources and perspectives. So it maximizes the LLM opportunities to link with other close knowledge. And so this is why scarce knowledge, commonly known as long tail knowledge, usually shows high hallucination rates, right? And another one is the lack of alignment. So now let's say the LLM is trying to follow your instructions and answer with the most probable response it has. But what happens if an LLM doesn't know how to follow instructions properly? So that is due to lack of alignment. So this alignment is a process that teach an LLM to follow the instructions and respond helpfully. So now you may have seen some models like we call that instruct models. So these models are trained on instructions and responses. So these models are able to follow the instructions. Likewise, so there are some LLMs that are uh, trained to do that. So those are more accurate in following instructions. And then we have another cause, poor attention. So this attention comes from the transformer. So these LLMs are created based on the transformer architecture. So there are encoder decoder architecture in these transformers, as well as decoder only transformers have been used to create these LLM models. And so if you look at attention closely, so there are some matrices called query keys and values. So this if the attention mechanism, so there are so if we need to understand complex relationship between words, in there we use a technique called self attention, and some reason models use marked self attention, and the earlier transform had self attention. So if this self attention could not identify the relationship between words properly, so it will provide you an token that is not relevant to the response. So this is mainly due to this hallucination due to this determined by the architecture and the hyperparameter choices. But we can avoid this by combination of fine tuning and some tweaks on the positional encodings. And but typically these poor attention based hallucinations are very often. And so you have been seeing that after a long conversation, so the model is unable to remember certain information that have been in the middle of a text, right? So that is due to the poor attention in the model. And the last one, the tokenize. So it is a core part of the LLMs, so due to its singular functionality. So it is the single component in the transform architecture, which is at the same time root cause for hallucinations and where hallucinations are generated. So if our tokenizer is not, so if the tokenizer is not able to divide these sentences into correct tokens, so the relationship between tokens will be incorrect. So the model cannot, or the our system cannot create the correct token, right? So now let's look at where these hallucinations are generated in the architecture. So I will give you some resources that if you want to learn more about these architectures, so you can follow these articles and learn more about the transformer and self-attention and mark self-attention mechanisms. So now when we talk about where these hallucinations are generated, So hallucinations can occur throughout the process to predict the next token in a sequence of tokens. So let's look in the initial phase. So as the sequence of tokens. Uh, so now when we have, let's say we have a sequence of sentences and these are split into words or subwords in tokenization, right? So then we are transforming these into numerical values. So this is the first potential source of hallucinations. So if the translation between the words into numbers are not correct, so there will be hallucinations. And then we have these encoded tokens passes through an embedding model. So we discussed about embedding. So the embedding layer needs to learn how to represent these tokens in a vector space where tokens with similar meanings are placed close and vice versa, as I mentioned earlier. So if this relationship is not good enough, the embedding vectors of two tokens could be close even though the tokens are not similar. So this could lead to hallucinations. So this will cause hallucination, and additionally embedding is used to represent the position of tokens in original sequence. So if this representation is not working properly, so the transformer not be able to understand the sentence properly. And then within this transformer block, so in this transformer block we have a layer for normalization and a linear layer. So this is a fully connected layer in a neural network. And then we have multi-head attention. So this is the self attention has been done for few attempts. And then we have fully connected layer again, and then we have feed forward layer. So here within this transformer block, and so it first undergo self-attention multiple times. And so when these interactions between the queries and keys values in this self-attention, so it is what determine which information is emphasized or prioritized and will carry more weight to those words for the final prediction. So if these values are incorrect, so this is where most factual hallucinations can occur. And also within the transformer block, the feed forward layer. So this has the role of processing self-attention output. And it is the layer that learns complex patterns over it and improving the output. But in that layer, it is very unlikely that it introduces a new hallucinations, but it will hallucinations, the hallucinations that are occurred in previous layers will be amplified, right? So these are the instances that in this architecture that hallucinations can occur. So now let's look at how to detect these hallucinations and improve your systems. So we have two techniques that we can detect hallucinations. And the first one is reference-based detection, and the next one is reference-free detection. So now if we look at reference-based detection, we have ground truth. So we can use this ground truth as the reference. So it compares the generated answers to a known reference using semantic and facts-based metrics. So there are key evaluation metrics in NLP. So blue scores, word scores, and these are like traditional NLP techniques that we can check whether the answers are similar to a ground truth. But now there are some recent metrics that have been developed in the community that we can use the check the accuracy of our answers using these metrics. One is answer correctness and faithfulness, and we can also use the context like context precision, context recall, like values to see whether our answers are generated from the given context or the answers are correct to ground truth. So there are some frameworks like DPWell or Ragas. So they have implemented these techniques. So we can use these frameworks to check whether our systems are working correctly and whether the answers are accurate. So when you want to get a number, so if you look at answer correctness, the range between the value between the range of these metrics are between 0 to 1. Faithfulness is also similar, and we have answer relevance, another metric. So we can give an accuracy for our systems. Also, we will be able to identify where the systems are not working properly and improve our systems. And so in order to avoid these hallucinations, so when you are looking these generative AI applications, we can use RAG-like systems. You may heard about RAG. This is called retrieval augmented generation. So we give knowledge sources that the information we want, and the LLMs have been used to generate the answer from these knowledge bases. So in there also, like when you're creating applications, so let's say we have some details about product and set of products, and if we have, so we need to have the same structure for the details. So if the structure for these details are different, so LLMs, there is a chance that the LLMs will be hallucinate even though you have given the correct context. So you may have retrieved the correct context from your documents, but still the generated answer will be hallucination because the structure of your knowledge base or the structure of the knowledge base is not clear enough, right? So you need to think about those things as well when you are creating generative AI applications. So now the next method is reference predirection. So now what we can do when we don't have uh, references to detect hallucinations. So in there we can use an LLM supervisor, and also so in there we use another LLM, a more capable LLM that can understand or get the context of the generated answers. So this next the other LLM is used to check the answers. So it is like critic agent. And then we can use the same LLM as a supervisor. So it checks the own outputs and check whether the output, the response is correct or not. And the best way is actually when you are before deploying these systems, we can do a manual check to get the accuracy of these systems. And even after deploying, we can have a section to get the feedback from the users of the systems. So here we can see that this is an example of this critique LLM. So now you may heard about the LLM agents, which are popular nowadays. So these agents can be used to improve the responses. And also we can use these LLMs in reinforcement learning techniques as well. So we can have a human in the loop to check. So it is not quite automating fully. So we are partially automating these systems. And if there is a decision that need to be taken, and it is a critical decision, so we can have a human in this loop to take that decision. So likewise, from these, we can improve our systems, and we will be able to identify the hallucinations or incorrect answers, and create more accurate and trustworthy AI applications. So now I will show you the importance of this tokenization and embeddings. So specifically the tokenization with Llama 3.1 model. So now there are a set of models, Llama 2 and Llama 3 open source models from Meta. So in these Llama 3 models, these models were able to have a higher accuracy than Llama 2 models, and they have changed the tokenization model of Llama 3 models. So I will show you the tokenization model and the keys in this tokenizer of Llama 3.1. and so it is the one in Llama 3.2 as well. And so let's check how this tokenization is affecting the responses. So I will show you that demo now. Hope you can see my screen.
Yes, Ishara.
Yeah, thank you. So here now I have an example for the tokenizer. So, so yeah, I'm going to install some libraries that are need to see these tokenization steps. So here I am using this Llama 3.1 tokenizer. Give me a second. So there was an issue connecting to the drive. So now it has been fixed. So now I have got the tokenizing model from the path, and so here now this tokenizer have about 128,000 tokens, and here I have added some special tokens and increase the size of this tokenizer. So now let's look at the values for some words. Now here I have got the uh, token ID for the word hello. So it is 15,339. So if we decode this one, you can see that we can get the answer. So here, if we look at this one, so now we can see that these two words have been tokenized into 4 tokens. So we know that this one belongs to hello, but the word Ishara is divided into 3 tokens. And now if we look at this one, so now here there are 18 tokens in this question. So in this prompt. So if we look at this prompt, we have the beginning of the text and the starting header and the whether this is from the user or the AI application, and this ending of header tag, and the question, this one, who wrote the book Charles Webb, and the end of these tokens, special tokens, and we have 18 tokens together in this entire prompt. So likewise, if we decode this one, uh, check the token number. So here we can see that these new tokens have added to the tokenizer model. And so let's visualize this one. So here you can see these are the tokens, separate tokens using this model. And so this is the word that had in the slide. So if you look at the tokens, so here we have, so this entire word has been divided into these tokens from this tokenizer model. So now let's look at what is the impact of this tokenization in when you are asking questions, right? So here I'm using the together API to get the endpoint for Llama 3.1 model. So there are 3 different models versions. So I'm using all of them here to show you that the impact of tokenization. So if we look at this one, so here now the question is, how many R's in the word strawberry? So this is the prompt we are going to use, and here the question has been added to this prompt. And the response from the Llama 3.1 model, there are 2 R's in the word strawberry. But if we look at this, there are 3. So why this has been not identified from the model? So if we look at the tokens in our prompt, so let's look at these tokens. So here we can see this is the new line token and the beginning of text and the user prompt, and this is the question. So this has been divided into these tokens. How many R's in the word strawberry? But if you look at the word strawberry, so this is a single token. So it is not able to identify, it is into more granular level. So now if we give the same question as this one, how many R's in the word strawberry with spaces between this word. So now here, if you look at the response, now here we can see there are 3 R's in the word strawberry. Now it has been identified that correctly. So if we look at the tokens in this prompt, so here we can see now the word has been divided into character level tokens since there are spaces. So so the model has been able to count how many R's in this word. So there are some examples for few more examples. So now let's talk about a math problem. So the question is which number is bigger, 9.11 or 9.9? So let's look at, we put the same question. So here that has been identified correctly from the Llama 3.1 model. So there are another 2 variations of this model, 70 billion and 405 billion parameter models. So let's look at the answers from these models. So you can see that 70 billion parameter model has been not correctly identified this one. If you look at 405 billion one, so it has been identified the answer correctly, but there are some information that are not required. So now why this is not working profile? So let's decode this into tokens. So now here we can see that the question, which number is bigger, 9.11 or 9.9? So it has been divided into these tokens. So the model would not be able to identify that profile. So here we can see that these are separate tokens, so it doesn't know that this is a single word, right? So it causes the LLM to give an incorrect response. And also another example is in string reversing. So if you look at this one, so now here the question is reverse the string, amazing. And you can see that this Llama 3.1 has been able to identify that correctly. And if you look at the response from 70 billion and the 405 model, so in this case, all of them have been able to identify this. So this is a common word and the models were able to identify that. But if we look at another word, so here, but this word is not identified correctly. The tokens are quite different. So now if we look at the word like language, so now here we can see what will happen in this one. So you can see it is not correct. So if we look at the tokens, so now here these Llama 3.170 and 4.5 models was able to identify these language word correctly. So we can see that if we look at the tokens, so this language word has been given as a single word, but this 8 billion model was not able to identify that. So here this language word has been given in between strings, right? So this is another example. Likewise, in these scenarios, you can see that the effect of tokenization is very much. So now, when we are creating these applications, we need to think about these as well. And so if you are expecting some answers, so there will be a effect from the tokenization as well. And so it is actually still processing, and here we can see that here it was not correctly identified. So when you talk about or when you think about the capabilities, so these capabilities depend on this tokenization as well. So let's go back to our slides and now we talked about what are hallucinations and how we can detect these hallucinations, right? So there are two techniques, reference-based and reference-free detection. So now when we talk about these hallucinations-free LLM applications, so it is just one piece of the LLM bird, and over time, with the growing availability of resources and invested in money and brains research in these topics, so it is not hard not to be optimistic that these problems will be solved in recent future. So now when you are creating applications, we need to think about this, and also we can use embedding fine tuning or rack-like applications to improve our responses. And in the industry these days, this fine tuning of LLMs as well as embedding models has been used widely. So it has been quite accurate, and it was able to improve the accuracy doing these techniques as well. And also, when you're creating these applications, we need to think about the accuracies. So we need to have a framework to detect the incorrect answers. So before deploying these into production, we need to think about the metrics like answer relevancy, faithfulness, and context vision recall. So there are open source frameworks to evaluate these applications. And also we can, so one of the main problems we have is we do not have enough data to check the accuracy of these applications. But these frameworks also support generating synthetic data. So we can generate synthetic questions as well as answer pairs and check the accuracies. And also we need to do manual checking as well, because we are relying on LLMs to do these checkings. So it is always better to check manually these applications before going for productions. So that is what I have to talk about these fundamental techniques like tokenization embeddings and how these are going to affect the LLM based applications, and how to detect hallucination and what are the causes for hallucinations, and how to reduce these hallucinations in your applications. So thank you very much for listening, and if you have any questions you can ask now. So if you have any questions, you can add those into chat as well. Any questions from the audience? And also, if you want to learn more about transformer architecture, so there is an article called The Illustrated Transformer from JRM. So it is one of the best articles I have seen for learning about transformer architecture. So you can refer those things. And also we have resource called Prompt Engineering Guide. So it has about most recent researchers as well as the topics that are going in the industry. So you can use these resources to learn more about those techniques and the architectures of these models. So it is always better to have an understanding about these architectures before you are building these applications, so you know what is happening inside your applications. Any other questions in the chat? So there is a question, to train or use these models, do we need to use paid services, or are there any free services to begin with? Yeah, so if you look at, so if you're creating conversational AI applications, let's say you are using rack-based applications, like these things. So we have frameworks like LangChain, Llama Index, which are open source. So you can use those things. And also we have open source models like Mistral models as well as Meta Llama models. So you can host, if you have enough GPU, so you can host these on premise as well, and you can use these to do inferencing with LLMs. And also there are some free APIs, like you can use Google's Gemini. So they provide an API key that you can use with your applications as an, so you can use Gemini models as an LLM. And also there is a platform called Grok. So they also support few models, some Mistral models, Llama models, and so you can try out. And they have a playground as well. So they have an API key as well, so you can integrate these LLMs into your applications to try out. So you don't need to depend on paid services. You can use these services to create applications based on these open source frameworks. And also all the testing frameworks that I have mentioned, those are also open source. So you can use these to build entire pipelines. Any other questions?
Guys, this is your chance to engage with an expert and dive into the world of AI. Don't hesitate to ask your doubts. We encourage you to share your thoughts and ask questions.
And also, if you have created these applications and if you are facing some problems, you can talk those things as well. So any experience from the audience who have developed some applications in generative AI side and some problems you are facing? Yeah, regarding these opportunities, so you can check with the HR teams, but actually I don't have an answer for that at the moment. So I think we do not have any other questions. So if you have any questions or need to discuss about these things further, so you can connect me with LinkedIn. So I will be there to discuss if there are any problems or any issues that you need to know about the areas of generative AI. So thank you very much for joining, and over to you, Fasan.
Thank you so much for the insightful session. Thank you so much for the insightful session, Mr. Ishara Neranjana, which enriched our understanding of this rapidly evolving field. And thank you for the engaging questions and thoughtful discussions. It looks like there are no more questions at the moment. Before we conclude, I had like to invite Kiran Sharma, the Assistant Secretary of IEEE, Student Branch of Rajarata University of Sri Lanka, to deliver the vote of thanks and officially close the session. Over to you, Kiran.
Thank you, Fasna. Good evening, everyone. On behalf of the IEEE Student Branch of Rajarata University of Sri Lanka, I would like to extend our deepest gratitude to all those who made today's event possible. First and foremost, I would like to thank our esteemed speaker, Mr. Ishara Naranjana, for taking the time to share his valuable insights on NLP fundamentals and how we can unlock the power of trustworthy and impactful AI. This session has been truly enlightening and it has provided us with much to reflect upon as we consider the future of AI. A special thank you goes to IEEE Young Professionals Sri Lanka and AI Driven Sri Lanka for their continued support and collaboration in making this event such a success. To all the participants, thank you for joining us today. Your enthusiasm and engagement make this event truly worthwhile. We hope today's talk has sparked your curiosity and motivated you to delve deeper into AI and NLP. Lastly, I would like to recognize and appreciate the incredible efforts of the entire organizing team. Without your dedication and hard work, this event would not have been possible. Thank you once again, and we look forward to seeing you at our future events. Thank you.
Thank you so much, Kiran, for the heartfelt vote of thanks. That brings us to the end of today's session, the AI Community Talk in December. We appreciate everyone's participation and hope you found the session valuable. Have a great evening, and we look forward to seeing you at our future events. Thank you.